Hello everyone, welcome to the sixth lecture of Tripoli 23, and the topic will be something you're already familiar with. It's on capacitance, but we're not gonna use it on a circuit. We're not gonna connect it to a voltage source or a current source or connect it to a resistor. No, we're gonna explain how capacitance or capacitors actually work. What creates a capacitance? Okay, so you can see here the outline of the of this lecture. Without further ado, let's dive into the topic. Capacitance is just basically two conductors that are separated by free space, or some they're separated by something that does not conduct any current, and that is actually dielectric if you think about it. So you're just considering two conducting surfaces separated by a dielectric medium. The first conductor carries a positive Q charge, while the second conductor creates a negative Q charge, and the potential difference between them is some voltage V sub O or V sub 0. The capacitance is defined as the charge stored in the conductor divided by the potential difference between the two conductors. So it's important to take note that the charges are equal in these two conductors right here. And it's also important that there should be no path for the current to flow between them. Okay, so basically any metal that has a charge, or any two metals separated by free space, or separated by a medium that does not conduct any current, create a capacitance. Okay, and basically um, everything metal that's not connected has a capacitance between them. All right, so that's your capacitance. Any metal in free space, any two metals in free space not connected to each other. So how do you quantify the capacitance in terms of the fields? So recall the integral form of Gauss' law. We can get the total charge using that by having a closed surface integral of the flux density with respect to your differential surface. And the potential difference between the two plates separated in free space, or a non-conducting medium, can actually be expressed by integral of d dot dl by just factoring in 1 over epsilon, where epsilon is the permittivity of the medium. Okay, so recall the permittivity which we discussed in the previous lecture. Okay, and this is dependent on the material. The capacitance, then, you just need to substitute Q over V. You get this expression here. So it's negative epsilon of the surface integral of d dot ds and line integral of d dot dl. Okay, so recall your resistance. Let's just compare it with the resistance. So the resistance is equal to, well, actually, something like this. Sorry, wait, let me just. So the resistance, if you remember, is equal to V over I, and this is actually equal to integral of E dot dl, okay, divided by the current is equal to integral of d dot ds, or sorry, E dot ds. It's related to integral of E dot ds, but you have a sigma factor at the denominator. Okay? So notice the similarities between them. If we get the reciprocal of resistance, which is equal to what we call the conductance, is actually equal to negative sigma integral of E dot ds divided by the integral of E dot dl. So it's striking how similar these two quantities are actually actually have, or how similar you can actually see that it's the conductance is a surface integral divided by a line integral. The capacitance is also a surface integral divided by a line integral. Okay, so there are actually similarities between them, which will go on in the future lectures. But let's just stop the discussion here. Just pointing out the similarities between them. It's kind of amazing. Uh, Anyway, okay, so forget all about that for now. Okay, let's focus on this one. Capacitance is basically a closed surface integral of your electric flux density divided by the line integral of your electric flux density multiplied by a factor of your epsilon. So the capacitance is actually dependent on the type of material. So there you go. So some remarks, the capacitance increases linearly as we increase the relative permittivity of the material separating the conductor. So if you have a better dielectric constant, if you increase the dielectric constant, you get better, larger capacitance. And although we see a flux density here and here, the capacitance will actually only be dependent on the material and the dimensions of the material. Okay, so well, if you have a uniform D, so where did that come from? If you have a uniform D, it will become something like this: D times S over D times L. D will cancel, and your capacitance will just be dependent on surface area and separation between the plates. For example, we have a parallel plate capacitor. So consider two planar conductors with area A separated by a small distance d. So this small distance ensures that the electric field that is not normal to the plates are negligible. Okay? The electric field that is not normal to the plates, something like this, is actually negligible. Okay? So we're only considering the electric field that is normal to both the parallel plates. Okay? So if there's free space between them, the total charge Q on one side, how do you compute that? Well, just form a Gaussian surface here. You can get Q, and it's equal to the flux density between the two plates times the area of the plate. V, in this case, can be computed the same. Okay? So you integrate that V from 0 to D. Okay? And that is equal to dd over epsilon sub 0. So to compute for the capacitance of a parallel plate, you get epsilon A over D. Okay? So quite easily done. Think about it. Alright. So uh, if we have a dielectric sandwiched between the conductors, so you'll have an additional flux between your plates due to the dielectric polarization, and the capacitance for a parallel plate conductor is epsilon A over D. The total energy stored inside the capacitor, so recall, to get the total energy stored, you just need to get the integral of your flux density dotted to your electric field intensity, and one half of that. So integrate that with respect to volume, and you get this expression right here. Since the field is constant inside the capacitor, your epsilon E squared will just be factored out, becomes 1 half epsilon E squared times dV, which is your area, times the separation. So it's the volume inside or between the capacitor, okay, between the two conducting plates. And basically you get this expression right here. Okay, so let's just manipulate that by getting d over d, multiplying d over d in the expression. Okay. So we have, let's try to make sense of why we did that. So let's rearrange the terms. We have e squared times d squared. That's this one. And we have epsilon a, so I'll underline it 2 times, over d, which is this one. So this is the capacitance, and this is the voltage squared. So the total energy stored in the capacitor is actually 1/2 capacitance times the voltage squared. Okay. An example, what is the effective capacitance of the parallel plate capacitor configuration below? So now we'll consider if the dielectric is discontinuous within the capacitor. What would happen? So we apply the boundary conditions. By boundary conditions, the flux should be constant as you cross the boundary. The flux, the electric flux density is constant. Therefore, the flux here at material 1 is equal to the flux at material 2. Let's call that D. The charge in one plate is by the boundary conditions here. There's no electric field at this point, and the charge density will be defined by the flux. Okay? The flux immediately at this point, which is D, times the area of your parallel plate, D times A. So the voltage can be obtained by adding the voltages across the two dielectrics. Okay? The voltages across the two dielectrics. How do you solve for that? So basically, you just integrate this from, let this be 0 and let this be D. Okay? And you separate that with D2, 0 to D2, and D2 to D. Okay? And since the electric flux is constant, so I'll just show you using word. Okay? So you won't be, what do you call this? Won't be confused. Okay? So recall that the voltage is equal to negative integral. Okay? So negative integral of your electric field dotted to your differential length. And here we want to integrate that from, okay, so the integral is from the final position, oops, the final position, let's set it here, from the initial position. So that's negative the integral from 0 to d. Okay, that's the potential difference between your point here at the top divided by the one here at the bottom. Okay. So to get that, well, you integrate it from 0 to d. Okay, is that correct? So correct me if I'm wrong. All right. So we can split this integral to two parts. So that is from 0, sorry, 0 to d2, and you have an electric field 2 at that point, and minus, sorry, d2 to d, and you have an electric field at that point, E1. Let's express that in terms of your electric flux density. Okay, so it becomes negative of the integral from 0 to d2, okay, E2 dotted to dl. So recall that our dl is from this point to this point, and our electric field is moving from this point to this point. Therefore, the dot product is actually negative. So this term becomes positive. So that's positive. Electric field is equal to your electric flux density divided by the what do you call this? the permittivity due to your dielectric 2, dl, okay, plus same here, but the dielectric now is divided by, is now E1, so the electric field 1 is D over E1, and that is from D2 to D. Okay, so you'll get that, you'll get this expression D times, so factor out D, you'll get D2 over epsilon 2 plus D minus D2 is actually D1. So that's D1 over epsilon 1. And this is now the voltage that is shown in the slides right here. So the effective capacitance is just Q divided by V, and that's A over D1 over E1 plus D2 over E2, which is equal to this expression right here. How did that happen? Okay, so let's back up. So we know the capacitance is equal to what we got earlier right here. So if we bring down A, so it becomes 1 over that expression times 1 over A. Okay, so you distribute A on both sides. Okay, so there you have A here on the denominator. You have A here on the denominator here. Okay, notice that this expression, epsilon A over D2, this is actually equal to the capacitance when we have this plate here and an imaginary plate within the boundary. Okay? If you have an imaginary conducting plate in the boundary, it's the capacitance of that distance of this uh, quote-unquote capacitor here. And if we have this expression, this is actually the capacitance if we have an imaginary plate at the boundary and this conducting plate at the top of your capacitor. Okay, so that's C1. Okay, so we have some form of capacitance here, C1. You have some form of capacitance here, C2. Oops. Okay, so yeah, you can understand that anyway. So kind of like this capacitor is just two capacitances that are in series, as evident in this expression right here, which is actually your parallel formula, quote unquote, for resistors. But we know that for capacitors, the formula is in series. Capacitor in series, the formula is kind of like capacitors in parallel. Okay, so that's how you can view this problem right here. So that's for your parallel plate capacitor. Let's now consider coaxial cables or cylindrical capacitances. Oh, give me just a minute. Okay, I need some. I'm gonna attend to some business. Right. Okay, so we're back. So consider the coaxial cables or cylindrical capacitors. So let the outer conductor have the higher voltage and the inner conductor be the lower voltage, as you can see in this the screen. So for a coaxial cable, so we have inner and outer, and the length for this coaxial cable is equal to L. The potential difference is equal to this expression here. Okay? So where did that come from? So recall that for cylindrical or for a conductor that is formed in a cylindrical manner. Okay. So recall that the electric field is equal to charge distribution divided by 2 pi epsilon. Let's put epsilon here to indicate that it's not just free space. So 2 pi epsilon times rho, and we have a rho as a direction right here. So yeah, there you go. This is the electric field due in the region between your inner conductor and your inner conductor here and your outer conductor here. So that region here. Okay. So in this case, the electric field is actually going inside since we assume that this inner conductor is negatively charged due to this voltage right here. So let me rewrite this. There you go. So we get the voltage across the two conductors. So again, it's the same formula right here. Oops, what happened? There you go. So it's the same formula right there. And your integral is now from, so we set the path to be from your initial point is here at the negative part, and your final point is here at the positive part. So that is from radius A to radius B. Okay? Radius A to radius B. So that's A to B right here. Since your electric field is, so recall, your electric field is going in and your path is going out. They have opposite directions. Then dl is in opposite direction with your electric field E. Okay? And this negative sign becomes positive. So we just substitute that. Okay? So magnitude of your electric field, and your dl becomes d rho because the path you'll take is actually along the radius. Okay? So that is now the voltage. So you can solve for the voltage here. Okay, you'll get uh, you'll get rho L over 2 pi epsilon ln. Okay, so this will be ln B minus ln A becomes ln B over A. Okay, and this rho L is actually equal to the total charge total charge BQ divided by the length of the cylindrical conductor L. Okay, so this is now where the expression came from. And to get the total capacitance, well, that's just Q over the voltage difference. So Q will cancel out and you'll get this expression here. So that's the capacitance for a cylindrical capacitor or coaxial cables. And coaxial cables actually have a capacitance. Right? And this will be significant when we'll be discussing how waves or your electric field and magnetic field propagates in your coaxial cables, but that's not important right now. Okay, lastly, we have a spherical capacitor. So we have a capacitor formed by two concentric spherical conducting shells. So kind of like your Faraday experiment from before. So it has an inner radius A and outer radius B, and between the spheres are dielectric or insulating materials. So these blue parts here are insulating materials. The outer shell is conducting. Right. The voltage here is Q over 4 pi epsilon times 1 over A minus 1 over B. Okay, so let's try to solve that. Recall for the electric field of your the electric field between the region here. So let this be positive and let this be the negative part. So the electric field is equal to surface charge density divided by 4 pi epsilon times r squared. So this is the electric field for the point charge. Sorry, this is not twice. It's the total charge. There you go. So the total charge that is actually on the total charge that is accumulated here within the conducting sphere inside. Okay, so that's the electric field. So we want to again get the voltage. So the voltage in this case, we integrate it from, since we set this as the positive, so we set this as the positive and this is the negative, we'll integrate from the outer radius, so that's B, the inner radius A. So from B to A, so the integral becomes negative integral from B to A, E dot dl. Okay. So the electric field flows from positive to negative. So it's something like this, but the path is going inside. Therefore, again, they're in opposite directions. All right. So your E dot dl becomes negative, and your negative sign will become, well, will become positive. So substitute that. You have the expression for E. So, and your dl is your differential radius. So that becomes dr. And that will be q over 4 pi epsilon, okay, times uh, negative 1 over r. Okay? So, there's something wrong. Oh, wait. Right, this is correct. Okay, so you integrate that from a to b. So this becomes uh, q over 4 pi epsilon. Okay? And that negative 1 over r becomes negative 1 over a plus 1 over b. Huh, there's something wrong. So, right, let me check. You have radius of a here, positively charged, and you start your initial position is from b, and you integrate to a, so that's integral from b to a. There you go. So initially negative integral from b to a, since the electric field flows from your positively charged to your negatively charged, then E dot dl is so this negative integral of E dot dl. So let me just use this. The direction is also your hat. All right, yeah. So if we get the dot product here, this will just become 1. Okay, so the negative will be retained. So this will become positive, and this is 1 over A minus 1 over B. Okay, so that's the voltage there. Okay, all right. So there you go. That's the voltage. Then you compute the capacitance. It's just Q divided by V, and it's Q divided by this expression. Q will be cancelled, and the capacitance for a spherical capacitor becomes 4 pi epsilon divided by 1 over A minus 1 over B. If the outer shell becomes infinitely large, Capacitance of the isolated spherical conductor. Okay, so infinitely large, you have a conductor, quote unquote, at infinity. Your capacitance will only be dependent on the radius of the inner conductor. That's 4 pi epsilon A. Okay. Okay, so just some notes, all right? So capacitance is measured in farads, and A is measured in meters. 4 pi is just a constant. So farads becomes your epsilon. What's the unit for epsilon? We don't know. Something times meters. That something is actually farads per meter. So the unit for epsilon is actually farads per meter. So it's different from what we knew from your force equation. So we knew that it's 1 over 4 pi epsilon sub 0 times some terms here. We can derive the unit for epsilon. Well, actually, that unit just becomes, from this equation, it becomes farads per meter. Okay? So, that is the end of this lecture. Okay? So, if you have any questions or comments, again, just comment away below in the comment section. I'll answer it as soon as possible once it is posted. So, I'll see you when I see you.